Was that muted?
No. Hello everyone, it's June 11th, morning session. Let's do this. Oh, what is this? Nothing of concern. Alright, let's take a look. Stone game. Oh my god, this is what, 7? Stone game number 7. Jeez. Okay, Alice and Bob come back again. Alice starts first. There are n stones arranged in a row. On each player's turn, they can remove either the leftmost stone or the rightmost stone from the row and receive points equal to the sum of the remaining stones' values in the row. The winner is the one with a higher score when there are no stones left to remove. Bob found that he will always lose the game, so he decided to minimize the score's difference. Alice's goal is to maximize the difference in the score. Wait, hold on. So Bob always loses the game, so he decided to minimize the score's difference. So between him and Alice. Alice's goal is to maximize the difference in the score. So we're not only doing who's gonna win, we know Bob is always gonna lose. So we're trying to, one person is minimizing, the other person maximizing the score. Given an array of integer stones, where stones I represent the value of the ith stone from the left, return the difference in Alice and Bob's score if they both play optimally. Oh my god. Okay, Alice removes 2 and gets 13 points. Okay, Bob removes 5 and gets 8 points. Alice removes 3 and gets 5 points. Bob removes 1, gets 4 points. Alice removes 4 and gets 0 points. The score difference is 6. We have 1,000 stones. They both play optimally. What is the optimal solution? Well, optimal will be each time for Alice is going to remove the smaller of the two, right? And for Bob is also going to remove. Why Bob remove 5? Why didn't Bob remove 4? If Bob remove 4, then he's going to get 9. That's why greedy doesn't work. And then Alice is going to remove 1. Alice is going to get 8. Alright, let's see. Follow your scheme. What's going to happen? So Bob's goal is to minimize the score difference. Alice's goal is to maximize the difference. You'll always lose the game. It's try to minimize. So Alice will go first, right? Or what if Bob wins? He's decided to minimize the scores different. So he wants to maximize himself and minimize Alice, and Alice is want to do the reverse. So 5, 3, 1, 4, 2. Let's say Alice go first. Alice starts first. So Alice starts first. The best strategy is, well, we take the smaller, right? So Alice and Bob. So first round, Alice get 13, yeah? Bob is 0. And Bob, why do you remove 5? Well, he removes 5 because he doesn't want Alice to get 5. Right? So if he removes 4, then he will get 9 points. But then Alice can remove 1, then Alice will get 8 points. Right? And then, let's do it this way. And then Bob removes 3, we'll get 5 points. And Alice removes 5, we'll get 0 points. And then Alice will have 21 in total, and Bob will have 9 in total, and the difference is 12. So the strategy, let's do this again. 5, 3, 1, 4, 2, right? So Alice removed 2, understandable, because But what if Alice removes 5? He can remove 5. He said, okay, I remove 5, so I make sure that Bob doesn't get. But there are only, each time there's only 2 choices, right? Yeah. So by removing 5, Bob gets slightly less, but then Alice won't be able to get 5. So Alice can only remove 3, right? Get 5. Alice can only get 5. And then Bob can remove 1, and Bob can get 4. Well, actually, if I choose 14, I can get 4. And that's 18 versus 16. Versus 12. That's 6. They both play optimally. Still, well, what do you mean by optimal? The score difference is 6, right? Return the difference if they both play optimally. Like in Alice's turn, right? Alice wants to maximize the difference. So she says, I can get. Why is that? Why is this the optimal for both? I mean, it's not optimal for Alice. Alice wants to maximize, but that's not her choice. It's Bob's choice, which means Bob doesn't play optimally. But Alice already does. So one person can only do all he can, and the other person can do all he can, and then that's what it means by optimal. So let's say if Alice removes 5, right? Then she gets what? 10. Then she gets 10 points, right? And then the 5 is removed. And for Bob, Bob can remove 3 or remove 2. Let's say he said, I want to remove 3. So Bob will get 7. And then Alice left with 1 for 2. And I said, okay, I don't want Bob to get 2, so I remove 2. So that gets 5. And Bob said I have 1 4. And then Bob said, I want to get, when you have 1 4, I always get the smaller because I want the largest. So Bob remove 1 and get 4. And Alice doesn't get anything. So it's 15 versus 12. 15 versus 11. Right? It's 15 versus 11. So that's so Bob is playing optimally. But does that mean Alice is not playing optimally? What does it mean by optimal? Like we have this 15 versus 11 result and an 18 versus 12 result, right? I mean, for Bob, he minimizes. He plays optimally. Hold on. Alice removes 2, and Bob removes 5, right? And Alice removes 3, and Bob removes 1. Are you saying that each time Alice is going to remove the smaller one so she can get a maximum points? And each time Bob's removing the larger of the 2, such that Alice cannot get the benefit of the large points until there are 2 stones left. If there are 2 stones left, then you always remove the smaller one. Is that how what it means by play optimally? So Bob will always lose the game, right? So that means even if he tries to get maximum points. So if you want to get maximum points, Actually, that's not getting maximum points, right? It's maximum points. Yeah, maximum points will be each time you take, this is 9, so you take, let's remove 2, right? And you remove 5. You remove 4, right? So you get 9. And then Alice remove 1. And then you remove 3. So that's 14, right? So 14. I think every time to get to reach the maximum for each one of them, you remove the smaller of the two. That's how you can get to the maximum. But that's not what Bob is trying to optimize. But because he knows he's gonna lose. So even if he tries to get to them, because Alice goes first, right? When Alice goes first, there's always a chance for her to get more points in the first round, right? In the first round. So remove something, you get a result. So for each round, that's true. Each round, Alice is always going to get more points than Bob for each round. You see, think about it. You have n stones, right? So the first round, Alice will pick any stone, and you have the remaining, and that's the score. And when Bob picks, the maximum he can get is the remaining minus one of the values. So Bob will always, each round, Bob will get less points compared to Alice. That's true. That's why Bob is always going to lose. And what if we have like this is odd and even, right? Even odd number, Alice will remove the last one. Alice will remove the last one. And even number, Bob will remove the last one. Right? Even number, like this is even number. Right? It's even number. Let's take a look at this. Bob will remove the last one if there are even numbers. And even number, which means the last one Bob removed, he doesn't even get any point out of it. And Alice will always pick the smaller one and get a big one. So yeah, so either Alice and yeah, so odd number, Alice didn't get the point from the last one, and from each play, she will always have more points than Bob, no matter what. No matter what she chooses, that does not matter. No matter what she chooses, to remove, and the remaining is the sum, and Bob has to remove anyone. So each time, right? Each time, Alice isn't gonna get something more than Bob. That's why Bob always loses. And even an odd doesn't matter because if it's even number, Bob's last is gonna be 0. So Alice can actually get 2 more chances than Bob to get points. If it's odd number, then Bob has 1 more chance to get, but still, you see, first time 13, Bob is 8. Second time, Alice is 5, Bob is 4. All right? And the last time is Alice is not going to get any points. So that means at each round, no matter which one Alice pick, all right? So the point of Alice is each round she wants to she wants to get the most. Let's say if that's the case, she wants to get the most out of it, right? So she can pick anyone and then get the result, the remaining value, and the remaining is what Bob is faced with, and Bob can pick one of the values out from the end. Bob can pick one of the values out, and then that will be the score. And we call it that's one round, right? That's one round. So Alice is gonna get some sum, right? Sum, and then Bob is gonna get the remaining sum. And the difference between the two, between the sum, is what is the difference between the two sums? So if Alex pick the rare, then the difference is, so if Alex picks the rare and Bob picks the rare, hold on, think about it again. Alex's goal is, but Alice goes first, right? Alice goes first, so he doesn't know. Like he picked front, or if he picked back. She picked front, she picked back. Does it matter to her? I mean, it doesn't matter if she picked the smaller one, then she gets a bigger sum, right? She picked the larger one, she gets a smaller sum. But her goal is to maximize the difference in score. If Alice picks the small one and she gets a large sum, and come to Bob, and Bob faced with this, and what he wants to do is to minimize the difference. Well, to minimize the difference, I think about it this way. Bob is always going to lose. That's for sure. So even if he tries to get the large points every single time, even if he tries to get a large point every single time, that's still not enough. But if you get the large one every single time, then he minimizes per round, right? He minimizes per round. Alice is going to go, but Alice is able to get more points in the next round because you're removing the smaller value, right? You're removing the smaller value. I don't know, like, what is the, I think I'm just, I'm stuck on what does optimal, how do I turn this into code? Maximize the difference in score and minimize the difference in score. Let's think of a simple case. Let's think 2 stones, right? 2 stones, N1 and N2, 2 stones. So Alice goes first. So Alice is always going to pick the large one because she wants to maximize. And Bob doesn't get anything. Bob will be 0, right? So the result, Alice will pick the small one. Alice will pick the small one, and she's going to be rewarded with a large value, and Bob picks, and there's nothing he can do. So the result will be the maximum of the two values in the array, right? That's 2 cases. What if we have 3, N1, N2, and N3? So Alice is going to pick. Alice is going to pick first. She wants to maximize the difference, so she can choose the smaller one, or she can choose the big one on the front. So if she chooses the smaller one, right, then Alice gets N2 plus N3. Let's say N1 is smaller than N3, right? And Bob is facing N2 and N3. So Bob have 2 choices, right? Bob can either pick the big one. If Bob picked the big, no, there's only 2 left, so Bob definitely picked the small one. So Bob picked the smaller of N2 and N3, right? Bob picked the small. Let's say it doesn't matter, N2 and N. So Bob picked the smaller of N2 and N3 and get rewarded the max of N2 and N3. Right, the maximum of N2 and N3. Let's say N2 is smaller than N3. So Bob picked N2 and Bob get rewarded with N3. And Alice picked the last one, it doesn't matter. So the difference will be N2, right? The difference between the 2 will be N2. Is this optimal? What if Alice picked the big one, and Alice is left with N1 plus N2, and And Bob is going, let's say n1 is also smaller than n2, and Bob's going to pick the small one, Bob's going to get n2. So the result is n1, the difference is n1. This is not optimal because Alice can do differently to make the results better, right? Yeah, Alice can do differently to make the results better. So I think optimal is if you, because let's say the other player always play optimally. So you play some certain way, and you have a result, and you change your play, and the results is better. That means your previous play is not optimal, right? Yeah, because here Bob is always playing optimally. With 2 left, he always chooses the small one, right? So Bob is playing optimally. So for Alice to play optimally, she has to pick the large one. If she picked the small one, then she'll get a smaller difference. And her goal is to maximize the difference. Okay? So that's with 3, right? That's with 3. So we do have the strategy. So what we have is, if we have 2, we have the best strategy for both of them, whoever picks. If we have 3, right? If we have 3, we also have the best strategy. Actually, we have to consider the other scenario where Bob picks first. So N1, N2, N3. If Bob picks first, what is he going to choose? But if he picks first, then what he can choose. So we'll say N1 smaller to N2 smaller to N3. So Bob can pick N1. Let's say Bob picked N1. Then his result is N2 plus N3, right? And Alice is left with N2 and N3. And Alice would pick N2, so remaining is N3. So the difference is going to be minus N2, right? Minus N2. If Bob picks N1, and Bob picks N3, that picks the large one, then Bob left N1 plus N2. And Alice is left with N1 and N2, so she picks N1, so she can get N2. So the result is minus N1, right? Minus N1. So in this case, Alice is always picking the optimal. So we can look at Bob. So the first, Bob get minus N2. So Bob want to minimize the difference. So Bob wants to be as big as possible. So the difference one is minus N2, the other is minus N1, and Bob wants the smaller one. The smaller one is minus N2. Minus N2 is smaller than minus N1. Right? Yeah, if you think about it in this case, both have some scores, and Alice get N3, and Bob get N2 plus N3. And that's N2. Right? The difference is N2. And Bob is N1. I think when 3 is left, if Alice picks first, Alice will pick the small one. If 3 is left for Bob, then Bob will pick the small one as well. Because if Bob picked the smaller one, he gets rewarded N2 and N3. And then the difference between the two is going to be N2, minus N2, right? Minus N2. If Bob picks N3, then the difference between the two will be N1, right? N1 is smaller than N2, so minus N1 is larger. So in Bob's case, if 3 is left, if we have 3 left, he shall pick. So let's try this. Let's give it 4, right? Let's try this case, right? And we know, like, if it's this case, then Alice will definitely pick 1. So Alice will be 8, and Bob will pick 3. So the result shall be 3. Oh, didn't return anything. I think this result shall be 3. Yeah, that's 3. So what if we do 4? Right? 4. So the current rule is if we have 2 left, so if I have len equals to 2, then whoever gonna pick the small one. If len is 3, then Alice go first. Alice gonna pick the small one, and the remaining is the same. If Bob go first, Bob gonna pick the small one as well. And let's say we have 4 values, right? M3 and M4. We have 4 values, and then let's just say like this: N1 smaller, N2 smaller, N2 smaller, N4, right? So we say Alice gonna pick N1. So remaining is N2, N3, and N4. In this case, Bob pick, right? So Alice is going to be N2 plus N3 plus N4. And then Bob, because we know it's 3, so Bob will definitely pick the small one. So Bob get N3 plus N4. And Alice with 2 left, Alice picked the small one, Alice get N4. Bob didn't get anything. So the result is N2 plus N4, right? If Alice pick the large one, right, other situation, if Alice picks the large one, which is N4, so Alice get rewards N1, N2 plus N3, and then Bob pick. And Bob would definitely pick the smaller one, so Bob get N2 plus N3. And then with N2, N3, Alice pick N2, so Alice get N3 left. So the difference between the two will be N1 plus N3, right? N1 plus N3. So it's either N2 plus N4 or N1 plus N3. So N2 plus N4 is, so Alice plays first, right? And then Bob always play optimally. So we need to find the maximum of this. The maximum is N2 plus N4, right? N2 plus N4, which means it's N2 plus N4, because that's larger, right? N2 plus N4, which means in the 4 case, Alice will go first, or Alice will pick the small one, right? Let's try this, right? So Alice go first. Alice pick small one. So Alice pick 4. So Alice gets 9, and Bob with 5, 3, 1. Bob picks a small one, then Bob gets 8, and Alice picked 3. So Alice gets 5, and Bob, last one doesn't really matter. So it should be 13, 14 minus 8 equals 6, and this one should be give us 6. Let's see if it's 6. 7. That is interesting. I thought it's 6. How'd you get a 7? So I say Alice is gonna pick the small one, and Alice is left with 9. Yeah. So I said Bob is gonna pick 5. If Bob picked 5, Bob left with 4, and Alex left with 3. Right? Bob picked 1, and Bob picked 5. Bob left with 4, and Alex only 3 ones because Alex has 3. So it's 12 versus 4. That's 8. That's 8. All right, that's 8. Well, given Alice's performance, Bob can definitely do better, because if Bob pick 1, Bob get 8. All right, and Alice pick 3, Alice get 5. So the difference, so in this case, the difference is 6. So yeah, we definitely improve. But that's not the answer, which means Alice should not pick the smaller one. Alice should pick the bigger one. But that's the only step that Alice can do differently. So if Alex picked 5, right? If Alex picked 5, so we'll have 8 remaining. And Bob with 3, 1, 4. Let's say Bob picked 3, and I get 5 left. And Alex picked 1, get 4. That give us 7. Right? Give us 7. Which means like this is better performance than a 6, which just Alex changed. So you're saying that what if Bob changed? So Alex picked 4, Alex picked 5, right? And Bob, I said I want to pick 4. And then Bob is left with 4, and Alex picked 1, so it's 3. That's 7 as well. That does not make a difference. But from our earlier analysis, Alice should pick the small one. Because if Alice picks the large one, right? If Alice picked the small one, she's left with N2 to N4, right? And then with 3 left, the earlier examined of 3 left, Bob, wait, which one did Bob pick? Alice picked 5, 3, 1, 4. Bob picked 3. Pick 3 or pick 4. Bob picked 3. Alex with yeah, that's actually the same situation. All right, let's do it again. So with 2, we're gonna always pick the small one, right? That's fine. With 3, I think just with 3 left, and Bob goes first. I say Bob will always pick the smaller one, because if Bob picked the small one, Bob get N2 plus N3. Now Alex get N3, and then the difference is N2. Right, the difference is N2. And Bob wants to minimize, and that is smaller. If Bob picked the large one, Bob left with N1 and N2. Alex picks N1. The smaller one. Yeah, the smaller one of the 2. It doesn't matter, it's just like the results will be, so N1, either N1 or N2. Either N1 or N2, so N1 will be like the 2 score is closer. No, it's not closer, it's like B is less big. B want to be like bigger, as big as possible, right? So we want the 2 difference to be big. So B has to pick the small one. Yeah, I think with 3, B has to pick the small one, and A has to pick the smaller one as well. So in this case, Bob picked the small one, and Bob get N3 plus N4. Right, Alex picks N3, Alex gets N4. So the difference is N2 and N4. Like, does the order matter? Let's order it how we would, like 1, 3, 1, 3, 4, 5, right? 1, 3, 4, 5. Does this give us the same value? It gives us 8. N2 plus N4. Yeah, that's 8. That does give us 8. But when the order changes, and the result changes, 5, 3, 1, 4. 5, 3, 1, 4. When the order changes, the result changes. When the order changes, let's just say N1, N2, N3, N4, and what we have is N1 is the largest, but the first round, say Alice picked Alice can pick M4. Let me just say Bob will always react optimally because we have 3. Actually, 3 is also going to be troublesome because if we have 3, there are different ways to organize the 3. So we have N1 and N2, right? One is large while the other is small, it doesn't really matter. And then the value in the middle. Now 3 shall be fairly straightforward. It doesn't really matter. Like if we do 3, 1, 4, right? 3 doesn't really matter. We always pick, if it's 3, it's 3, and Alice picked first. Alice always picked the smaller one. And Alice picked the smaller. So if I have 3, N and N2 and 3, doesn't matter the big. So Alice picked first. Alice will pick the small one. So Alice get the N2 plus the maximum of N1 and N3, right? And then Bob will pick the smaller, so Bob will get the max of N2 and N3, right? So this is, if Alice picked first, that's one outcome. And the other outcome will be Alex picked the large one, so Alice will get N2 plus Alex picks the large one. So minimum of N1 and N3, right? And then Bob will get the max of N2 and Bob will get the max of N2 and the pick the max, so the minimum of N1 and N3. Right, this we can compute. I still want to compute for all these cases. I mean, it's a sliding window, right? So how do we compare? So this Alice goes first, and we guarantee that Bob is the optimal. So if Alice goes first, what we want to see is the maximum, right? So that's like this. Or no. If Bob goes first, well, we can actually know who's gonna handle this. So if it's like even number, if it's odd number, right? If it's odd number, Alice is gonna pick 2, so Bob gonna pick 3. Okay. Okay, let's do this. So it's 4, right? 4, we know Alice is going to difference of the score, and then plus Alice's score. Yeah. So if it's 4, right? Alice goes first, so we know that Bob's gonna pick the last 2. Bob's gonna pick the last one. So Alice is 4, Bob is 3. No. Alice picked 4, right? Bob picked 3, and Alice picked 2. Alice picked 5, Bob picked 4, Alice picked 3. Now Alice do this. Alice picked on 5, right? And then Bob pick on 4, and Alice can pick on 3, and Bob pick on 2. Yeah, Bob pick on 2. If it's odd number, then Bob pick on 2. If it's even number, Alice gonna pick on 2. Right? That's where we start. So when we given this, it's even, so Alice is going to pick on 2, right? So we know Alice is going to pick on 2. So we just say 5, 3 will give us a difference of 5. 3, 1 give us a difference of how do we represent this? This is indices. Indices. Bitmap. Oh no, but we are talking about 1,000. No, bitmap is not going to work. 1,000, that's too big. What are the ways to? I just need like 2 numbers. I need 2 numbers. I need a way to get 2 indices, right? 2 indices into a key. How do you do that? 2 indices into a key. Like easier way to get 2 indices into a key. Only way I can think about is tuple, right? A tuple is the easiest way. What are the other ways? Oh, are you sure? Complex number? Oh, hold on the stall. Let's first figure it out. Like, so we know this is the Alice's difference, right? So Alice's difference. So just Alice minus Bob. Alice minus Bob. So we say Alice minus Bob. At the end, there's a 3, and 1, 4. Let's give us 4, right? So Alice minus Bob, we know. Now we have 3. We have 5, 3, 1, and 3, 1, 4. This time Bob goes first. So when Bob goes first, Bob can go 5. If Bob goes 5, Bob gets 4, right? So Alice minus Bob is minus 4, right? And then Alice is 3, 1. Alice can be 3. So this one will give us minus 1. And if Bob goes 1, right? Bob goes 1, then Bob gets 5, 3 is a difference of minus 8. And 5, 3, Alice gets 5, so that's minus 3. And Bob wanted to minimize, so minus 3 is the result. So if it's 3, 1, 4, if it's 3, 1, 4, Bob goes 3, that's going to be minus 5. 1, 4, Alice gets 4, so that's minus 1. If Bob goes 4, then the difference is minus 4. And Alice gets 3, 1. That's 3 minus 1. So this one is minus 1 no matter what. So that's good. Now let's look at 5, 3, 5, 3, 1, 4. All right, 5, 3, 1, 4. Alice goes 4. Right, so Alice gets 9. The difference is 9. And Bob is getting 5, 3, 1. And Bob can get minus 3 out of it. So this one is 6. And Alice goes 5. Then Alice gets 8. And Bob is 3, 1, 4. So Bob can get minus 1. So that's 7. Right? And we want the maximum because, yeah, we want the maximum because it's Alice's turn. So this one is going to be 7. So the answer is 7 for this. I think I solved it. My God, this is hard. Yep, this is hard. Well, what's the runtime? O(n) squared. It's a sliding window. So we go from 2, 3, 4. So it's n minus 1 plus n minus 2 plus all the way to 1 as O(n) squared. Yep. All right. I have confidence in the accuracy of this one, but takes so long. All right, let's get this one done. Yeah, it is dynamic programming. You know what's gonna be funny? What's be funny is after all these thoughts and if you run it and it failed. That would be funny. It's so funny that I don't even want to laugh. All right. So here's the deal. We know. So how you gonna save it? So we're gonna have a DP. It's gonna be a dictionary. Then what? Then we want to know who's gonna do what, right? Who's gonna do what? So we're gonna say if it's odd, then Bob picked 2. So we're gonna say even or odd. Is even, I just call it is even, equals is odd. It's odd is easier. Is odd gonna be landstones. I'm pretty sure we have to go landstones multiple times. So let's just do landstones, right? And then say n mod 2. If it's 1, and it's 0, then it's always false, right? So now I'm gonna say pairs. Actually, we only need the 1 letter because we know the length, right? We know the length. We actually don't. We need to have 2. No. The row is going to be the length. The column is going to be the. So now we can do. Okay. Hold on. Don't speak. The length for the length is going to be the size. The size is going to be the maximum is n. So for this in range n, okay, yeah, I can do it this way. So in range n, so we have n rows, right? Let's do n plus 1. Let's do n plus 1 because the last one is the length. So rows are the length. So row index is the length, and column index is what's column index? Column index is the index of the left. The leftmost index is the leftmost index. Oh my god, I don't even understand what I'm trying to say. Alright, so the column index is the leftmost index of an array of stones that has length of the column index. Right. Hopefully it makes sense. So the maximum, right? The maximum you can get is from 0 all the way to n, all the way from 0. That means 0 times. Actually, we're gonna go. That's fine. I'm gonna go 0 times n. Right? If we go 0 times n, then the last will be n minus 1. Right? This last will be n minus 1. N minus 1 with 2. Yeah, that's okay. All right. Then what do we do? Well, is odd, right? If it's odd, then we're gonna start with Alice, right? If it's odd, let me see. No, if it's odd, Bob gonna pick 2, right? Bob gonna pick 2. So, how should I put it? let's do this later. So okay, now we're gonna say for L in range from 2 to n plus 1, 2 to n, right? That's the I. Let's do I. This is the row, which is the length, right? Which is the length. And then for j in range from 0 to n minus I. Hold on, is n minus I? Well, it is n minus I. Yes, it's n minus I because the last one j can take is n minus 2 if we want to get 2, right? That actually means this is not going to be n because the last one is n minus 2. So it's actually n minus 1. You can get a bit smaller, right? And then we're going to start. We're going to fill it in. So we say dp. If I equals 2, then dp ij gonna equal to what? Let's get it true or false, right? Let's get equals 1, right? So is odd is going to be true. Is odd. It will be Bob's turn. Bob turn, right? Bob turn. And then this is going to equal to, if Bob is on the last turn, then the result is going to be the maximum, right? The maximum of stones I and stones I. No, J plus I. Is J plus I? Well, 0 and 1. Well, actually no, I start with 2. So I have 2 stones, right? So J plus 2, that's 0, 1, 2. So we have to minus 1. Right, have the minus 1. So the maximum of these two, if Bob turn, right? If it's Bob turn, then we get the maximum of this, but we're gonna get a minus on it, right? It's gonna be a minus on this because we do Alice minus Bob. Else, so let's just do it once. So max val equals this thing, right? And it is going to be max val if Bob turn, else not Bob turn, it's Alice turn, so then it's just going to be max val. So that's if I equals 2. If I is not equal to 2, depends on which turn it is. So after that, we're going to say Bob turn equals not Bob turn. Right? If Bob turn is true, the next one will be false, and it's not Bob's turn. If Bob turn is false, the next one will be true, and it will be Bob's turn. So next, actually, I think we have to do this for everything. So we're gonna just put it at the end. So now we go to I equals 3. So we have 3, right? So I have 3. It depends if it's a Bob's turn or if it's not a Bob's turn. So we're gonna say if Bob turn, right? For 3, if it's Bob's turn, then Bob can do 2 things. Either take one or take the other, right? So I'm going to say Bob going to choose the smaller one, right? Bob going to choose the smaller one. So let's say Bob choose the smaller one, which is so Bob choose smaller one. If stones I and j is smaller or equal to, it doesn't really matter, stones j plus I minus 1, right? If that's, then Bob choose the smaller one, so Bob choose stone j. So we say temp value, so temp equals to sum, right? I mean, we can even make it faster if we do a prefix sum. If we do a prefix sum, that will make it faster. Okay, let's do a prefix sum as well. So we're gonna say presum equals accumulate, right? Which is from itertools import accumulate. So let me just say accumulate stones, right? And then we'll list this. I'm not 100% sure, so I'm gonna check here. Itertools import accumulate a equals 1, 2, 3, 4, 5, and we say accumulate list accumulate a 1, 3, 5, 1, 3, 6, 10. Yeah, that's true. So when accumulate, so presum, so we don't have to calculate the sum. So the temp, so not temp, Bob val equals presum. So pick j, so it's going to be j plus I minus 1 minus minus presum j minus 1. If j is larger than 0, else 0. Right? If I pick j, no, it's just minus j, because it's like I take j away, right? So that's the Bob value, this current Bob value, and we're left with so we know it's called best optimal Bob is this, right? And then optimal Alice Ale is going to be dp I minus 1, right? I minus 1, and then because we picked j, so it's going to be j plus 1. So it's optimal Ale, optimal Bob, and then the result is going to be, so optimal Bob is going to be, we're calling it a minus. It's going to be a minus value, yeah. And optimal Ale is this, and then Bob, if this case, Bob choose smaller one, right? Bob choose smaller one, then optimal alley is this, then you have to say Bob turn, right? Bob val equals, find a maximizer, math.inf, right? Math.inf, because we're gonna get import math. So Bob val is this. Bob choose a smaller one, and then we say Bob val equals the minimum of Bob val. Now let's just say it's complicated. So let's say Bob small equals optimal Bob plus optimal Alex. All right, so this Bob choose smaller one, and Bob can also choose larger one. If Bob choose the larger one, then optimal Bob is going to be, so Bob choose the larger one, so stones j plus I minus 1. So this is going to be pre-sum j plus I minus 2, right? Minus pre-sum j minus 1. Now here we're going to do if j is larger than 0, else 0. So we're going to have to this, right? And then the whole thing going to be minus, because Bob's optimal Bob and the optimal Alex is in dp, same thing, I minus 1. And because I pick j plus I minus 1, right? So it's going to be j, right? It's going to be j. It's going to be j. Okay, so this is going to be Bob large equals let's also small, right? Small equals optimal Bob small, this is small, and then this is going to be large, and Bob large, small. Yeah, I like to say LG, large equals optimal Bob large plus optimal Alice large. And then we're going to say man, we have to do the same thing again for the other way. Oh, it doesn't really matter. It doesn't really matter. Just like I pick one or I pick the other one. It doesn't really matter. So I just pick one. So Bob choice 1, right? So Bob choose left. There we go. Bob choose left. And this is going to be L. Bob choose left, right? So Bob left is going to equal to left and left. And this is Bob choose right. It doesn't matter large or small. If Bob choose left or Bob choose right. And all of this is going to be right. And Bob choose right, and then going to do this. And then it's Bob turn, then we say dp I j, right? dp I j equal to a minimum of optimal Bob left and optimal, not optimal, just Bob left and Bob right. So Bob left and Bob right. So that's if it's Bob's turn. If it's not Bob's turn, so we're going to copy the entire thing. So if it's not Bob's turn, so it's Alice's turn. So Alice choose left. So that's the same thing, right? Yeah, that's the same thing. That's the exact same thing. So it's not going to be whose turn here. Whose turn is going to be determined at the end. So we just say choose left, right? Choose left or choose right. So choose left when they say optimal left, optimal P1 left, optimal P2 left, and then the optimal left is going to be optimal P1, player 1 left, and optimal player 2 left. And here is, let's say, choose right, and then that is going to be optimal player 1 right, optimal player 2 right, and then this is going to be optimal right. This is going to be optimal P1 right and optimal P2. Oh, there is a difference. Because if it's Bob and if it's Alice, let's do it this way. So P1 and P2 is going to be like this, right? P1 is going to be, well, if Alice goes first, then the optimal is still going to be optimal plus, because I'm going to save the negative value no matter what. So hold on. Let's not consider the Bob and Alice at this point. Let's just get the optimal, right? So optimal left, optimal right, optimal right, optimal left. Then it depends, right? It depends. I think we don't need this. We don't need this. So if it's Bob's turn, right? Then we say this is gonna be the minimum of optimal 2 left, player 2 minus, actually I want to be more explicit. It'll be minus optimal player 1 left plus optimal player 2 left, and this is going to be minus optimal player 1 right plus optimal player 2 right. Else, if it's not Bob's turn, then we're going to get a maximum because it's Alice's turn. So Alice wants to maximize, right? So when she maximizes, it's going to be optimal P1 left plus optimal P2 left, because I saved the negative value in it. So it's just Bob is going to be negative, Alice is going to be positive. And I'm going to do this thing here. Alright, so after choosing, after done, then Bob's turn equals not Bob's turn. So now we go up, 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 all the way. So this is the table. Once we're done, right? Once we're done, we're gonna get our result at, I'm gonna return dp n, right? So length is n and 0. This is from the start. Okay. Exciting moment. Here we go. Let's test. Oof. So 5, 3, 1, 4, 2. This one shall give us 6, right? Next one, 7, 90, 5, 1, 100, 10, 10, 2. This one gives us 122. And I have a couple more that I deal with ourselves. So 1, that's a 5, 3, 1, 4. This one gives us 7, right? This one gives us 7. And I remember if we do 1, 3, 4, 5, that one gives us 8. Okay, that should be sufficient. So stones. This is a stone game. 7 stones. All right, check it. And we got 0. What the hell? That is not how I expect it to be. Hold What the actual hell? Alright. Not right. There's something wrong with the DP, which is fine. Let's just print out the DP table, just kind of inspect. Right, I'm gonna print for row in DP, print row. We did not put anything in it. We only have an 8 here. Huh. Alright, this is not right. Let's take a look again. So we have 0, 1, 2, 3, 4. That's right, 1, 0, 1, 2. So this is the first level, right? If I equals 2, max value is still on j from 0, and 0. Why the result is 0? What the hell? Let's print dpij 0 and 0. Oh, I put double. Damn. All right. Still not right, but we get something. We get something. So let's see. We have. It's 1, 2, 3, 4, 4. So it's even number. So it's Alice's turn, right? Even number. So it's Alice's turn. So it's Bob's turn. It's not Bob's turn. I'm gonna get the max value. But why would we have a negative value? Huh? Why would we have a negative value? Because I do Bob turn right here, which shall not be happening inside, which shall happen here. Okay, so we got 5, 3. The last one is 0, which should not be 0. And minus 2. I think it should be plus 1. Right? Because that's the range. So if we do n minus 2, that means we can only get n minus 3. So we need to get n minus 1. So that's the j range. Okay, let's try it again. There we go. Now we pass. We pass this one. And let's not print anymore. Now we pass everything. Okay, I have confidence in this. It'll take us a long time, but this one looks promising. Let's go. Pending. Judging. Oh my God, I think we have a wrong answer. Oh! I just took a long time. Wow, we passed. But it took a long time. Oh my God. We are at somewhere here. Oh, not too bad. I thought it was horrible, but it's not too bad. So what we at is 4,420 milliseconds. Jeez. And that's actually scored a 69% ranking. I think this is a hard question. So it's not simple. At least for me, it's not simple. But this is still DP, right? The idea is to find out the optimal the score difference, right? Find out the score difference between Alice and Bob at each possible arrangement of stones. That means we start from 2 stones. What is the score difference if Alice goes first, and if Bob goes first? Then we do 3 stones, and so on and so forth, until we get to the entire set of stones. At each stone arrangement, a player, can take the left or right stone. After the player makes a move, we already have the score difference of the remaining stones, right? How the score difference if the next player plays optimally. Thus, we can compute the 2 score differences for the current player if he chooses left or right stone. He or she chooses the left or right stone. For Bob, he needs to minimize the score difference, so he will choose the move that minimize the he needs to minimize that yields the min of he will choose the min of the 2 scores. For Alice, she will choose the max of the 2 scores. We build up a DP table with row indices, row index being the length of any stone arrangement, and column index being the leftmost index of the current stone arrangement. Right? The result is dp and 0. Runtime is O(n) squared, and we hit a 4420 milliseconds, or a 69% ranking. I mean, I definitely see this one. We can optimize the space complexity to get to only 1, right? Because every time we only go 1 up. So we can use, let's try it. So solution 1, space complexity is O(n), and space complexity is O(n) squared, which we can improve to O(n). Let's do that. Let's improve the space complexity to O(n). Same solution as above, but with 1D DP table, DP array. Okay, so this one, these are the same, so we don't have to use this anymore. So DP is just going to be an array. So it's just this one. Right? It's this one. Bob's turn, fine. And then if it goes to 2, then you just say dpj equals this. Else, we do this. This is going to be dpj plus 1, right? This is going to be dpj, and then dpj equals this, and dpj equals this. I want to return dp0. So 2, pass. Okay, so yeah. I mean, we can even make it like we can write it another way. So instead of doing this, right? So we just say nah, but we have to do extra check. Let's put it out, right? Let's put it out, and what we're gonna do is we'll do this. And then we don't have to do this. Right, and then for j, 2, so -1, right? Because we cannot hit n-1. Yeah, so it's the first. So this is like the base case, right? This is like the base case with 2 stones. So max value is going to be this, and then dbj is going to be this, Bob turn, and then we're going to say Bob turn equals not Bob turn. And then we go in. Now we don't have to do this anymore. So we can directly do this. But we can actually put this one up in here. So we don't have to do this. Right? Pre-sum dp equals this. I want to rearrange this a little bit. dp equals this. Base case with 2 stones, and this is going to be from 3, right? From 3. We change the turn. We go left and right, and then I think this one I before. Okay, this is not I. This is just going to be j plus 1. Yep. So this is solution 2 with one array. Actually, I want to let's do this. Submit. Pending. Judging. I don't see it any faster. It's pretty slow. But space complexity is definitely low. Oh no, it is faster. Much faster. Look at here. We hit, yeah, 1D array. This one we hit 81. So 3840 milliseconds. 81% ranking. O(n) squared, runtime, O(n) space complexity, and like this. Very good, very good. All right, let's take a look at the actual one. Wow, I hope this one is a hot one. It took so long to deal with. Stone Game 7. It's a medium one. I thought it's a hot one. All right, fair enough. Took us an hour to figure it out. All right, that's a good question. Yeah. I can see the. I think I can see the space compartment. Memory. Yeah, right here. See that? 14 megabytes. This is 38 megabytes. That's a tremendous difference. This is dynamic programming. What are the hints? Constraints are small enough for O(n). Yeah. Try using dynamic programming. Yeah, that's it. bottom up, DP. How to avoid TLE? Well, you probably need to use the presum to avoid TLE. Because if you calculate the difference, maximize the difference among two choices to play optimally. Result, yeah. But they didn't do. We just go maximum. Hold up. They didn't go choose left. No, that's choose left. Right? Yeah. Choose left, choose right. Minus dpi. We just pick the maximum of this. dpi plus 1. How'd you get a dpi plus 1? Oh, from bottom up. That's when the dp 0. That is so simple, huh? minus 2. To 0. And what is I? I is the index. J is the length. No. J is not the length. J is the end point. That's the indices. Oh, I and J are the indices. I is the front, J is the back. Okay, so plus 1. So we're gonna say we're gonna get a maximum of this minus this. But you don't care. You don't care who is doing what. Like if Bob's doing this, Bob gonna minus Bob's score, Alice's score. So you don't care about who is doing this. Just every time you're gonna get a current. You're gonna get a current. I really think about it. You're gonna get the current player. Current player. J plus 1. Let's pick the left, and then going down is gonna be I plus 1 J, or I J minus 1. Yeah. So that's just the current score. So dpij records the best score that anyone can get at now the best, well, that's not the best score, the maximum difference. The maximum difference any player can get. If I'm Bob, right? If I'm Bob, then if I'm Bob, that is this minus the next one, yeah. And if this, yes, for Bob wants to maximize his difference, right? Yeah, so it's unified. Both of them wants to maximize the difference. Both of them wants to maximize. Yes, both of them wants to maximize the difference. It's just the Alice, the difference. So the Bob wants to minimize the difference, of the total score, but he wants at each step, he wants to maximize the score that he can get versus the next one. That makes total sense. Oh, always taking the maximum. At time of Alice, we're maximizing, which will inherently minimize Bob next pick. Can't take the maximum 2 out because that will be negated on the level above. Yeah, I think I got, because see what I have is a minimum of this, and we're saying this is the positive value, and this is a positive value, and then we get negative. So the minimum of these two is a maximum of this minus this, right? The maximum of this minus this. And because we're doing the minimum, then what we put into it is a negative value. And so this one is actually this minus the positive here. We'll use the plus. So we can combine these. Let's see, the magic is right here. Magic is right here. We can do max, right? Minus and minus. And we don't really care whose turn it is, right? We don't care whose turn it is. And then on the first level, it's just going to be max, right? Again, we don't care whose turn it is. Does not matter. This is going to be max, right? And this, so we don't need a turn, right? We don't need a turn. I think this one shall stay pass, yes, which we can even simplify here, right? Stones j plus 1, so we can do is this, dp is going to be this, right? For I in range n minus 1, and when you say max this for it. So we don't even need, so this is going to say the base case to 2, so we don't even need this. And then reference before, there's no j, so there's going to be j here. There we go. That's the thing. And right, in this case, if we do a 0 plus, then we don't even have to check here. Right? We don't even have to check here. We're converging into the good solution, right? And if this is the case, we can further put them into one line. We can just say, choose left, optimal player 1, optimal player 2. No, I like this is more explicit. Yeah, so update the solution posted here. The solution posted here clarifies an important point. We do not have to keep track whose turn it is, because at each turn, any player wants to maximize the difference between his or her current point and the next player's optimal, right? The next player's optimal difference, right? Optimal difference. Yeah. wants to maximize the difference between his current point, the current point I get, and the next round the player will get an optimal difference. So I want the difference between the two, right? And then this is the optimal difference that I can get, right? So for Alex, I got a point, and the maximum difference, the optimal difference the next player can achieve with a certain value. So then the optimal is me minus the next difference, right? Me minus the next difference. If the next difference is positive, which means Bob is doing better, right? Then I minus the Bob's difference, and then that's the new difference. If Bob is doing worse, which means it's a negative value, right? Then I get even more. For Bob, it's the same thing, right? Bob has current value, and Alice has the next one, right? And then Bob is minus Alice. Yes, and the player wants to maximize the difference between his current point and the next players, and the next rounds, not players, next rounds optimal difference. In other words, both Bob and Alice's goal is actually to play optimally. To play optimally. To play optimally. Despite, in other words, despite the goal of both players are different, they are essentially doing the same thing. To maximize the difference between their current point and the difference between their current point and the difference and the optimal difference in the next round. Since we do not have to consider terms, the solution can be vastly simplified. Yep. So this one, I'll run again. Oh, this guy is also pretty good, huh? Wow, this DP took a lot of efforts. I got a wrong answer. What? This is not expected. We get a wrong answer. I thought these are the same. Oh, something is different. That means I haven't understood fully if this happens. Oh, hold up. It passed earlier. Now I say it didn't pass even these test cases. What? Oh, because of this. I see. This one threw me off. Nope, 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 no, 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 nope, 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 nope. I do not like it. I'd rather do another check. I'd rather do another check. Nope. I mess around with the indices. Like I have to like shift the indices. I don't want to shift the indices. Because if I shift the indices, it just makes things. Oh no! This one is not right in the right position. Unexpected indent. I think it'll be faster. Well, I got fewer things to handle, so I hope. Yeah, it is faster. Slightly faster. All right. I think that shall be it. I mean, we did capture the gist, but we have this turn thing, right? The turn thing is just like the key is to realize these two are the same thing. Line 49 and line 51, these two represent the exact same thing. That is the max of this minus this. That's the key. Now once you realize that, you're like, oh, we don't have to include the turn at all. Everything else is standardized. All right, only one more post. Do memorization by hand. Change none. Use classical DP table. I'm so used to area cache. Going to sum minus minimum this and this. Minimum. Let's see. What's A? A is the input. I and J. What's I? I is the two indices. So pick AI, right? So AI plus, this is the current sum, and this is the next level, and this is the next level. But cumulative sum J plus 1, right? J plus 1 minus I. That's minus I. That's we pick I. So we always pick I. How we pick J? That's weird. Yeah, I don't want to think about it. You know, we have a good one. I just want to imprint this in my brain. All right. Yeah, that's it. That's it for today. I'll see you guys tomorrow. Adios.